Before we can look at where we're going, we have to recognize where we came from. An ancient pre-Scholastic Greek philosopher, Empedocles, proposed that light has a finite speed. A century later, Aristotle insisted that light is a presence and not a movement. Neither of these proposals had any evidence. Therefore, for 2,000 years, the argument continued until Ole Romer started observing the eclipse of Jupiter's moon's Io. He noticed that Io's eclipse, when Earth's orbit was perpendicular to the line of sight, was 11 minutes later than when Earth was in conjunction. Allowing an Earth's radius of 11 light minutes, the speed of light is calculated to be 220,000 kilometers per second. This discrepancy to modern values could be due to the accuracy of his clock over the course of 3 months and Io's elliptical orbit. Nevertheless, it was finally demonstrated that light had finite speed. "52 years later, James Bradley used the aberration of light to determine the speed of light to be 295,000 kilometers per second. In 1983, the CGPM defined the speed of light to be 299,792,458 meters per second. And of course, in 2017, the team of LIGO Virgo verified that the speed of gravity was also equal to the speed of light. Since light having velocity had the unexpected side effects of delaying Io's eclipse, it's a wonder that no one considered that the consequences of gravity having a finite speed, especially that gravity of an object would be delayed by where the object was observed, not where it actually was. Of course, at low, near-zero velocities, the difference would be impossible to measure. However, once an observed object reaches speeds of a few percent the maximum speed of light, this delay must be taken into account. So that brings us to our ideal scenario, where we have two objects, A and B, heading towards each other. And since the velocity of gravity is reduced to the maximum speed of light, I will define that the time it takes light to travel the sum of uppercase d and lowercase d to each object will have traveled lowercase d. Consequently, when the objects are a distance d apart at locations A and B, A will visually see B at B prime, and B will visually see A at A prime. Not only that, but A will gravitationally perceive B at B prime, and B will gravitationally perceive A at A prime. And this has some pretty severe consequences. If we plug in the perceived distance d plus d into the Newtonian equations without time dilation, the force, which equals mass times acceleration, is also equal to the product of universal gravitation and the two masses divided by the square of the perceived distances between the objects. This reduces the Newtonian force when compared to instantaneous gravity, which reduces the respective acceleration, which reduces the change in velocity, which reduces the change in kinetic energies. To summarize, in a two-bodied system where the masses are the same, ma equals mb, and the objects are approaching each other, then the perceived acceleration, which is based on the perceived distance of d plus d, is less than the expected Newtonian acceleration, which is based on the actual distance of d. Therefore, the increase in kinetic energy, which is also based on the perceived distance of d by d plus d, is less than the loss of potential energy, which is based on Newtonian kinetic energy, which is based on the actual distance of d. This isn't a tragedy, because Newton's special relativity, using the Lorentz factor, also had loss of energy related to velocity during the descent. Now let's look at the ascent of the two objects after the energy conserved bounce. Again, I will define that by the time light travels a distance of uppercase d subtract lowercase d, each object will have traveled a distance lowercase d. Therefore, A will visually see and gravitationally perceive B at the closer location B prime, and B will visually see and gravitationally perceive A at the closer location of A prime. Therefore, instead of having the value uppercase D plus lowercase d in the divisor of the equation, we have the smaller value of uppercase D subtract lowercase d. This means that not only is this the acceleration not equal to the acceleration of the descent, it is greater than the deceleration expected using just Newton, and it is much greater than the acceleration experienced during the descent. Rather than retrieving energy during the ascent that we lost during the descent, energy is lost in both the ascent and descent. To summarize, in a two-bodied system where the masses are the same, ma equals mb, and the objects are receding from each other, then the acceleration, which is based on the perceived distance of d minus d, is greater than the expected Newtonian deceleration, which is based on the actual distance. For there to be conservation of energy, then the deceleration of the ascent should be equal to the acceleration of the descent. Instead, just like the descent, the ascent also has a loss. Therefore, the decrease in perceived kinetic energy, which is also based on the perceived distance of d minus d, is not only greater than the loss of potential energy, which is based on Newtonian kinetic energy, which is based on the actual distance of d, but is also a loss of energy, just like the descent. Since energy is lost in both the descent and ascent, it is obvious that energy is not conserved. By assigning the ratio of kinetic energy of the object's velocity over the energy of the maximum speed of light to be less than 1 over 1/1000th, we calculate that the object's velocity must be less than 3.14% of the maximum speed of light, where the law of conservation is a good approximation to within 1/10 of 1%.